Welcome to the fascinating world of waves. Waves are all around us, from the gentle ripples on a pond to the invisible signals that power our smartphones. In physics, a wave is a disturbance that transfers energy from one place to another without transferring matter. Waves can travel through solids, liquids, gases, and even through the vacuum of space. Understanding waves helps us unlock the mysteries of sound, light, and even the very structure of the universe. In this chapter, we'll explore what waves are, how they behave, and why they are so important in both nature and technology. Wave is characterized by several key properties: amplitude, wavelength, frequency, and speed. Amplitude refers to the height of the wave. Wavelength is the distance between two consecutive crests or troughs. Frequency is how many waves pass a point per second, and speed is how fast the wave travels. These properties help us describe and measure waves in various contexts, from ocean waves to light waves. By understanding these characteristics, we can predict how waves will behave in different environments and applications. Waves can be divided into two main types: mechanical and electromagnetic. Mechanical waves, like sound or water waves, need a medium such as air or water to travel through. Electromagnetic waves, such as light, radio, and X-rays, do not require a medium and can travel through the vacuum of space. This distinction is crucial in understanding how different waves interact with their surroundings and how we use them in technology and communication. Waves can also be classified by how they move. In transverse waves, the particles of the medium move perpendicular to the direction of the wave, like ripples on a pond. In longitudinal waves, the particles move parallel to the direction of the wave, as in sound waves traveling through air. Understanding these two types helps us analyze wave behavior in different situations, from musical instruments to seismic activity. Wavelength is a fundamental property of waves. It's the distance between two consecutive points that are in phase, such as two crests or two troughs. Wavelength is usually measured in meters and is crucial in determining the energy and behavior of a wave. For example, shorter wavelengths often mean higher energy, as seen in ultraviolet light compared to visible light. Measuring wavelength helps scientists and engineers design everything from musical instruments to wireless networks. Frequency tells us how many waves pass a given point in 1 second. It's measured in Hertz Hz, where 1 Hertz equals 1 wave per second. Frequency is directly related to the energy of the wave. Higher frequency means more energy. In everyday life, we encounter frequency in music, pitch, radio stations, and even the colors of light. Understanding frequency helps us tune into the right signals and appreciate the diversity of waves around us. Amplitude is the maximum displacement of a wave from its rest position. It's a measure of how strong or loud a wave is. The greater the amplitude, the more energy the wave carries. For example, louder sounds have higher amplitudes, and brighter lights have greater amplitudes. This property is vital in understanding how waves transfer energy and how we perceive them in our daily lives. Wave speed is how fast a wave travels through a medium. It's calculated by multiplying the frequency by the wavelength. Speed equals frequency times wavelength. Different waves travel at different speeds depending on the medium. For example, sound travels faster in water than in air, while light travels fastest in a vacuum. Understanding wave speed is essential in fields like communication, navigation, and even medicine. The principle of superposition states that when two or more waves overlap, the resulting wave is the sum of the individual waves. This principle explains many phenomena, such as the patterns created when two stones are thrown into a pond. Superposition is key to understanding complex wave behaviors, including interference and resonance, which we'll explore in the next scenes. When waves meet, they can interfere with each other in two main ways. Constructive interference happens when waves combine to make a larger wave, while destructive interference occurs when they cancel each other out. These effects are seen in everything from noise-canceling headphones to colorful soap bubbles. Interference patterns help us understand the complex interactions between waves in nature and technology. Refraction is the bending of waves around obstacles or through openings. This phenomenon explains why we can hear someone speaking even when they're around a corner, or why light spreads out after passing through a narrow slit. Diffraction is a key concept in understanding how waves interact with their environment and is fundamental in technologies like radio transmission and optical devices. Reflection occurs when a wave bounces off a surface, like an echo or a mirror image. Refraction happens when a wave changes direction as it passes from one medium to another, such as a straw appearing bent in a glass of water. Both reflection and refraction are essential in understanding how we see, hear, and use waves in daily life, from eyeglasses to sonar. The Doppler effect is the change in frequency or wavelength of a wave in relation to an observer moving relative to the source. It's why an ambulance siren sounds higher as it approaches and lower as it moves away. This effect is used in radar, astronomy, and even weather forecasting to measure speed and movement. Standing waves are formed when two waves of the same frequency and amplitude travel in opposite directions and interfere. This creates points that appear to stand still, called nodes, and points of maximum vibration, called antinodes. Standing waves are seen in musical instruments and many physical systems, helping us understand resonance and sound production. Resonance occurs when a system is driven at its natural frequency, causing it to vibrate with greater amplitude. This is why a singer can shatter a glass by hitting the right note, or why bridges can sway dangerously in the wind. Resonance is a powerful phenomenon that can amplify waves and is crucial in engineering and music. Musical instruments work by creating and manipulating waves. For example, a guitar string vibrates to produce sound waves, while a flute uses air columns. The pitch, loudness, and quality of the sound depend on the frequency, amplitude, and shape of the waves produced. Understanding wave principles allows musicians and engineers to design instruments with unique sounds. Wave-particle duality is a fundamental concept in quantum physics. It means that particles like electrons and photons can behave both as waves and as particles. This duality explains phenomena such as interference patterns in light and the behavior of electrons in atoms. Wave-particle duality challenges our classical understanding of physics and opens the door to the strange world of quantum mechanics. Electromagnetic spectrum includes all types of electromagnetic waves, from radio waves to gamma rays. Each type has a different wavelength and frequency, giving it unique properties and uses. For example, microwaves heat our food, infrared is used in remote controls, and X-rays help doctors see inside our bodies. Understanding the spectrum helps us harness these waves for communication, medicine, and more. Waves are powerful carriers of energy and information. Whether it's the warmth of sunlight, the sound of music, or data sent through fiber optics, waves move energy and messages across distances. This ability makes waves essential in everything from natural processes to modern communication systems, shaping the way we live and interact. Modern communication relies heavily on waves. Radio, television, cell phones, and the internet all use electromagnetic waves to transmit information quickly and efficiently. By modulating the frequency, amplitude, or phase of waves, we can encode and send vast amounts of data across the globe. This technology connects people, businesses, and cultures like never before. Wave energy is a promising renewable resource, harnessing the power of ocean waves to generate electricity. However, it's important to consider the environmental impacts, such as effects on marine life and coastal ecosystems. Careful planning and technology can help minimize these impacts while providing clean, sustainable energy for the future. Waves are not just a topic for scientists, they're part of our daily experience. From the sound of a friend's voice to the sunlight streaming through a window, waves shape our senses and our world. Recognizing the role of waves in everyday life helps us appreciate the science behind common phenomena and the technology we rely on. Medical technology uses waves in many ways. Ultrasound waves help doctors see inside the body, while X-rays and MRI scans use electromagnetic waves for detailed images. Even treatments like radiation therapy rely on wave principles. These applications show how understanding waves leads to better health and improved medical care. Nature is full of waves, from ocean tides to seismic waves during earthquakes. Animals use sound waves to communicate and navigate, and plants respond to light waves for growth. Observing waves in nature helps scientists learn about the Earth and develop new technologies inspired by natural processes. Technology harnesses waves in countless ways. Wireless communication, medical imaging, and even microwave ovens depend on our understanding of wave behavior. Engineers and inventors use wave principles to solve problems and create new devices, making waves a cornerstone of modern innovation. Mathematics provides powerful tools for describing waves. The wave equation relates wave speed, frequency, and wavelength, allowing scientists to predict how waves will behave in different situations. Mastering these equations is essential for anyone studying physics, engineering, or related fields. Waves behave differently depending on the medium they travel through. For example, sound travels faster in solids than in gases, while light slows down in water compared to air. Understanding these differences helps us design better materials and technologies, from soundproof rooms to fiber optic cables. Industries use waves for a variety of purposes, including non-destructive testing, quality control, and communication. Ultrasonic waves can detect flaws in materials, while radio waves enable wireless control of machinery. These applications improve safety, efficiency, and productivity across many sectors. As our understanding of waves grows, so does our ability to innovate. From quantum computing to renewable energy, waves are at the heart of many emerging technologies. By studying waves, we prepare ourselves for the challenges and opportunities of the future, making science and technology more exciting than ever. In this chapter, we've explored the many facets of waves, their properties, types, and behaviors, as well as their crucial roles in nature, technology, and society. Waves are not just abstract concepts, they are the foundation of much of the world around us. By understanding waves, we gain new insights into physics and open doors to endless possibilities in science and innovation.